Thank you very much. Is the microphone on? Yes. Should be. All right. So today I'm going to tell you basically what's in the title, applications of these symmetric functions, mostly Schur functions that I told you about last time. Certain extensions and generalizations and some open problems, but they're going to be intermixed, so there is not going to be different sections for each. So you will see, however, the different sections are going to be different types of applications. So this talk basically is going to be structured into 15-minute chunks of this, that, and so on. And the idea is, these are a lot of slides. There is a lot of information. So the goal is that you guys can make connections and recognize things as they appear. So we're not going to do the computations. This is going to take too long to do any of those. But the point is that something's possible. All right. So I will start I'll move along in historical terms, what came first. So let's look at this problem that I mentioned last time, the longest increasing subsequence of a permutation, right? Here is the definition. You have permutation, which is just a bijection from the numbers from 1 up to n to 1 up to n. You write it in line notation. And we're looking for the largest case such that there are increasing subsequence of indices such that the values of W are also increasing, okay? They don't need to be consecutive or anything. So the question was, what's the distribution of this longest increasing subsequence? And Hammersley, in the 50s, so towards 60s, he wrote, so some of this is rigorous, some of it is more heuristic analysis, but the expectation, at least, somewhere on the order of square root of n. So, of course, what are we doing here? We're choosing W uniformly at random among all permutations, right? And so this is our observable as the longest increasing subsequence. Okay, so the way he did it was, so first of all, he was using the Erdős-Sékérés theorem to show that this should be on the order of square root of n, or maybe larger. And then he was doing some Poissonized two-dimensional process, which heuristically would tell you that this should look like that, but he couldn't get this constant C1 and C2. Or whatever the more precise asymptotic. So how do we do this? We do this with the tools that I showed you last time. So if we take a permutation, there is this RSK algorithm which sends it to a pair of standard Young tableaux, right? Everybody remembers these are so Young diagrams of the same shape filled with the numbers from 1 up to n increasing along rows and down columns. And what was one of the good properties of RSK is that the longest increasing subsequence of the permutation is equal to the length of the first row. So in this case here should be 3. And let's see if it's true. Well, 1, 2, 3 is the longest increasing subsequence here, and we cannot find any longer, so it's 3. And so basically, the longest increasing subsequence is equidistributed with lambda 1, but how is lambda distributed? This lambda is a partition, again from last time. Well, it's distributed according to the number of pairs of standard Young tableau of this shape, which we denoted f of lambda, right? So, and of course, divided by n factorial.
Sorry, is it always true that in the first row you see the longest increasing subsequence?
No, not at all. There's just an accident here, like bad example. Yeah, you cannot actually see the longest increasing subsequence.
146 as well.
Yeah, 146. Yeah. actually, yeah, no, it's no, you don't really see it from this, yeah. And so this measure here, so first of all, this is a probability measure. It might not be obvious, but last time we wrote this identity, right? So it does sum up to 1. This is called the Plancherel measure. So let's try to analyze what happens with this. Okay, so here is our setup. We're looking at the standard Young tableau of a given shape. The shape here is 2, 2, 1. These are all 5 of it. What do we know from last time? We know how many there are. There is a Hook-length formula, which in this case looks like this. So we go over all the boxes in Lambda, and we count the box to the right and below. These are the hooks. And so this is a nice product formula. We can actually do some asymptotic analysis on it. And this is what Vershik and Kerov and separately Log and Shep did. So under this Plancherel measure, so the probability of lambda is equal to f lambda squared over n factorial. This is how the typical partition would look like in the end. So remember, this is different from the shape that Igor was talking about. I'll show you in a moment. And also, what is the typical f lambda gonna be equal to? Well, it's actually gonna be around square root of n factorial and then lower order terms of the scale minus square root of n. And in fact, they proved that the maximal f lambda satisfies this inequality, but for 2 constants C0 and C1. Okay, so let's be a little bit more precise. So first of all, we are going to rotate the shape to look like this. This is a Lego tiling of our friend Dan Betea, which is in IHP right now, I think, still. So this is a random partition generated by our friend with this limit shape. And this is what the limit shape equation is. So it's not very nice. It's this curve. What we need to realize is that this is only between square root of minus square root of 2 and plus square root of 2. It's actually intersecting here. It's not, if you remember the other case with the random partitions, it would go to infinity. Here it's intersecting. And this is what we mean by converges. The typical partition under this shape converges to this. Actually, there is some pretty precise bounds. If we scale it by square root of n, this is the ith part of lambda minus the value of that function. This is actually less than some constant n to the minus 1/6. So this is our epsilon is actually of this order. Okay, so where is lambda 1? Lambda 1 is this part, right? Well, it depends. It's symmetric, so it doesn't matter which direction we look at, but lambda 1 is the length until it reaches this axis here. So what is it? Well, square root of 2 should be. So this actually gives us the lower bound on the expectation. And actually, the upper bound can be derived with more elementary means. And that both of these combined gives us that lambda 1 is approximately 2 square root of n. So square root of 2 here, but there is another square root rescaling. That's why we get 2 instead of square root of 2. And by the way, these things that I'm saying, these are in, so I wrote some references here people were asking. So yesterday was mostly this, enumerative combinatorics. There is also MacDonald, but I won't really get to the more complicated stuff here. This is our former postdoc from UPenn, Per Alexanderson. So he created a whole website, symmetricfunctions.com, which has all sorts of things. And then this thing is from Dan Romik's book on the longest increasing subsequence. Mostly. Okay. So what's next? So first of all, there is already an open problem, but before I state it, so this is what I said earlier. If you look at what's the maximal value of f that f lambda could take, it's sandwiched between the two terms that look like this. So square root of n factorial, and then e to the minus square root of n plus lower order terms, so some constant. And actually, if f lambda has similar asymptotics, then we know actually lambda is going to be within epsilon of this curve. So there is a relation back and forth. And so what's the open problem here? The open problem is that to show that if we do the precise asymptotics of this maximal dimension, it is going to be square root of n factorial e to the minus c square root of n plus lower order terms. So that basically asymptotically this c1 and c2 are the same. Still an open problem. Why, if you try to do this with the Hooke-length formula, you will realize that so in the Hooke-length formula, when we turn the diagram like this, it looks like a curve, piecewise linear curve going up. It's the slopes 1 and minus 1. So the limit curve, of course, is something continuous. And when you start moving boxes around here, you'll realize that the error introduced that goes towards the integral is very close to the square root of n. So you're getting into a very fine territory. And just to say a few words, how did actually Vershik and Kerov do this? So if we parameterize this like this, and this is our boundary is some function g. So the reason we rotate it is so we don't have singularities, so that this function becomes actually continuous. It doesn't have jumps. So now it is continuous, almost everywhere differentiable function. This is our limit shape. And let's say that we have our parameters. What is the Hooke length in terms of this? It is basically, I mean, it's proportional to the distance, horizontal distance, because everything is 45-degree angles between these 2 points. So let's say that this is S and this is T. So F lambda is, so of course we're going to take a logarithm, so that's, having a product formula is nice. So this is going to be log n factorial minus log of all the boxes, of course. And what are this HU equal to? Well, if we are approximated with a continuous integral, this S of u is going to be exactly S minus t, the distance between st, whatever square root of 2 if you want, or 1 over square root of 2. But how do I know that this is actually a Hooke? So if I take a point here and a point here, these are not going to give us these are not going to give us a box. Here we need to make sure that one of the slopes is 1 and the other one is minus 1. So 1 minus g prime t, okay, plus 1 minus g prime of s. This is going to be non-zero exactly when we have a situation like this. And then we have ds dt, and so we can solve a variation of calculus of variations to find the minimizer of this function. So we're not going to do that, but that goes beyond the combinatorics, so no, we're not going to cover that. Okay, so this is this is how we can get that information, but what's next? I mean, we have expected value of lambda 1. Can we actually figure out the distribution? Turns out we can. This is it. So I actually have been to so many talks that mention the airy kernel and airy function without ever writing it down. So I decided to write the whole beautiful thing down just so you can appreciate it. So this is a theorem by Bike-Deift and Johansson from the 90s. And that is that if we subtract the mean, so which is 2 square root of n of our longest increasing subsequence, divide by n to the 1 over 6, so we are in the right scaling regime. So that probability less than or equal to x is converging to f2x. It's called a Fredholm determinant, which comes from some operators, can be expressed as determinants, and it's also known as the Tracy-Widom distribution of the maximal eigenvalue of a Gaussian unitary ensemble matrix. So longest increasing subsequence is behaving like the largest eigenvalue of a random matrix. And so here is the definition of this function. So it's certainly not obvious that this is a distribution function. So on this, there should be a plus here. But anyway, how did they do this? So they didn't really use the Hooke length formula. They used a different formula, which comes from the Jambeli identity, which Jean was asking me about. So it's not the product formula, but it's actually a determinantal formula for f lambda. That somehow, well, you have a determinant here, so you need to, there is a lot of analysis to be done. So this is, of course, very technical, but using a different formula for f lambda. Okay, so the next thing I wanted to talk about is more applications of the symmetric function theory to Lozenge tilings, and there are numerous of them. So I, of course, am going to be biased and tell you for the ones that I worked with. But any questions so far about this? Yeah?
How does this, so compared to what we saw on Monday, is the difference that here we're picking a random permutation?
Yeah, exactly. The measure is different. So it's the Plancherel measure. So you pick a partition with the weight proportional to f lambda squared. Otherwise, we pick a partition with weight 1, uniformly random partition, and the whole thing changes completely. So this is a lot more complicated in some sense. So the partitions, the integer partitions were easier. You can pick some two geometric random variables to approximate them and so on. You cannot really do this here. Not to my knowledge. Okay, so I said one magic word, GUE, Gaussian unitary ensemble. So there are random matrices here, and they're gonna be. And also these functions are not surprisingly connected to Lozenge tilings as well. I mean, the whole thing somehow lives in the same world, even though it's not, the connections are not always explicit and apparent. So let's look at Lozenge tiling. So this is a picture from Liu's simulations. So this is a very large Lozenge tiling. So let's say we're tiling the hexagon n by n by n in this case. And let's zoom into the boundary here and see what it looks like. If you zoom in, it's going to look like this. With this type of constraints, we are always going to have one horizontal lozenge right next to the vertical line. Then we're going to have 2, 1 below, 1 above, and so on, 3, and so on and so forth. What's the combinatorial constraint for their position? So these x's denote their heights on this axis, if you want. the constraints are this. This is what's called interlacing. So you can write them on a triangle, and they're going to satisfy this inequality. One is between the other. So just like visually on the picture, that's how they're relative to each other. So what is the joint distribution of these numbers with the appropriate whatever shifts, rescalings, and so on? And it was conjectured by Okunkov and Rishitekin that this thing converges to the Gaussian unitary ensemble, again, the same random matrices. This, with the appropriate rescaling, these behave like the eigenvalues of principal submatrices from this ensemble. And so this was done long time ago for the hexagon by Johansson and Nordenstam, and then we did some more general domains in various different ways. There is connections to the sixth vertex model and so on and so forth. So a lot of people in this audience have worked on these types of problems. So I will tell you one approach to this, and there are others, of course. But before we do that, let me define these random matrices. After all, there's a GU Gaussian unitary ensemble. There are Hermitian matrices, so complex. The entries are complex numbers. The ones on the diagonal are IID normal, and the other ones have real and imaginary part, also IID or normal with different variants. And so we are choosing these entries according to these distributions, and we start looking at the eigenvalues of the submatrices, the 1 by 1, 2 by 2, 3 by 3, and so on. So we get vectors of numbers. Of course, because these are Hermitian, the eigenvalues are going to be real. So we can actually order them. And so this is more of a linear algebraic fact that they are going to interlace as well, just like the picture I showed earlier, this time for the eigenvalues. And so this vector of random variables that we are obtaining this way is going to be the GUE corners or minors process. We're going to denote by GUEK. So how do we get the convergence for the Lozenge tilings? One way is to find some kind of probability generating functions for what's going on for the positions of lozenges, and this is where combinatorics and the symmetric functions come in. But before I do that, let me tell, so this, we can do this for tilings with various symmetries as well, so vertically symmetric, centrally symmetric, and so on. And how do we parameterize the whole problem? So we're going to do it like this. We're going to take what's called a trapezoid. So here we have 3 flat boundaries. And here on the right side, we are going to fix where these horizontal lozenges are. Their positions. This is going to give us a partition, lambda. So what's the partition here? So this is 0, this level 0, so it's 0, 0, then we go up 3, then 3, 3, and then 1 more up, then we have 4. 4, 3, this is our partition. And then we look at all tilings of this domain. So here is how we get the hexagon with this parameterization. We set everything to 0 here and everything to whatever other A, in this case 8 here, then gives us flat piece, and the rest have a hexagon to tile. So the real restriction is that we need a flat side somehow to make this, and otherwise it's actually not true. And so here are the statements. So if we have tilings of the hexagon, if we have this boundary here, lambda converges to some limit function. We have this behavior if we have the centrally and vertically symmetric Lozenge tilings, we can also say this. And how do we do this? Also, actually, we also can do the limit surface. So shape is maybe not the right word here. So surface, this is a stepped surface, and the whole Lozenge tiling converges to that. But I would imagine that Liu will talk more about this later this week. So I'm not going to spend any time on this. I'll just show you about how to get the GUE with Schur functions. So here is our setup. Lambdas are on the right boundary. Here we have flat boundary, and we form a semi-standard Young tableau out of this picture. How do we do this? If you actually look at the 3D picture from one side, you are going to basically see a semi-standard Young tableau where the entries here are going to be given by the levels of the flats that you see. But the other way we can do this is we look at the vertical lines here. The first one has a lozenge at position 3, so let's make a partition 3, just one number. The second one has lozenges at positions 5, 2. We make a partition 5, 2. Then the third one is 5, 4, 1. We make a partition 5, 4, 1. We draw them as Young diagrams, and we stack them on top of each other. And this configuration here ensures that what you get once you stack them up and you write the corresponding numbers in these boxes that are visible after you stack them up, this is going to be a semi-standard Young tableau. So weakly increasing along rows, strictly increasing down columns. And what's the last shape? Well, the last thing is the green line here. It's going to be our lambda n. OK, so what if we want to look at the lozenges that occupy the first k vertical lines? We're going to look at the entries in the semi-standard Young tableau, which have values from 1 up to k. And so the probability that the first k numbers occupy a given shape, nu in this case, is going to be cut off a nu here. So it's going to be the number of semi-standard Young tableau of this shape with k entries, and then the number of skew semi-standard Young tableau occupying the rest of the shape. So here nu, you can think of k equal 3 and nu being 5, 4, 1. We're looking at this shape. The rest is a skew semi-standard Young tableau, which is basically the Schur function, skew Schur function evaluated at 1, 1, 1, whatever, many times. OK, so now we are moving on towards more algebraic methods. So now we're going to do something funny. We're going to take the expectation of the following function. So y1 up to yk are just variables. Our random variable is going to be this nu, which in this case I denote xk. So expectation with respect to uniformly randomly chosen tiling with boundary lambda. And this is our random vector xk. And we can plug in a function of an actual polynomial here. We can still do that. So this is like a moment generating function, but instead of having monomials here, we have Schur functions. So why do we do this? Because things simplify when you sum up over all possible nu here that you can get. You actually get a ratio of 2 Schur functions. One is evaluated y1 up to yk and then once, and the other one is just 1. So this is what we call a normalized Schur function. So think of this is an analog of a moment generating function, except that you are modifying your variable. So it's a certain type of transform of our probability measure. And then we can actually, well, we can calculate it in all these cases. So in the case I showed you, we have S lambda, so ratio of 2 Schur functions. In the other cases, we have also something specific. These are orthogonal group characters. This is this thing squared, and so on and so forth. And now we can do some asymptotic analysis. So, we can, how do you prove law of large numbers, for example, with moment generating functions? Is the same thing we're going to do here. So first thing is so we can always define a Schur function by the well-determinantal formula to have arbitrary exponents, real numbers. So in this case, if these nu are distributed according to this Gaussian, to the vector of eigenvalues for the GUE, then we actually get this formula. So this should remind you of normal distribution, moment generating function. And that's why Gaussian, right? So that it's not an arbitrary thing. And then we can do the same thing for the tiling. We have to do some rescaling, subtracting, and so on. But in the end, we get things to converge to the same thing. So we can actually say that our random variables, which were the positions of the lozenges near the boundary, converge in distribution to the eigenvalues of this Gaussian ensemble matrices. And so this is the final statement. Any questions so far? Yeah?
Do you see somewhere some kind of these matrices from the tiling? Is there
That's a very good question. I've been thinking about this for a while, and it's not clear at all how you see that. In fact, it's not clear at all, even from the standard Young tableau lambda 1, and this, it should be a direct connection, but it's not. Somehow when the measure changes, the discrete picture is changing, you don't really have anything.
Well, there is a connection between longest increasing subsequences and matrix integrals.
Yeah.
For a long time.
For matrix, but integrals, right? So it's not, you don't really see the actual matrix. Yeah. Yeah, because the formulas, so there, we know actually the exact distribution function. So this is actually an easy computation, which I'm not showing. So you have all these joint distribution functions of these random matrices. They're very nice, and they resemble, like, there's Vandermonde in there. There are all these things that show up in the computation with Schur functions as well. So you can actually do the computation, but you don't really see conceptual.
The answer to this question might be that instead of a matrix, you should think about representations.
Yeah, but even that is not, because the Haar measure on general linear group, this is a different random matrix.
Now, there is a setup to put both on the same footing when you are looking for invariant measures on matrices versus invariant measures on matrices versus representations of infinite dimensional unitary group.
Okay, so
you can put both in the same framework.
So the answer lies somewhere in the representation theory that's governing the whole. So I'm not gonna. So there is also a way to do the limit surface using this Schur generating function, various convergences, and I'm not going to go through the details of this. I'm gonna leave it. So I'll post the slides. Of course, you can see what this is about, but you do the counting measure for each line. The discrete measure, you can show that it converges thanks to this Schur generating function. Part of the reason this works is that this is symmetric, actually. So somehow even if you know it at k variables, you know it at any k variables in some sense. So this is giving you a lot more information. Okay, and this is how the limit surfaces would look like if you calculate so you get an implicit equation for the limit surface from that thing, and it's not your friend. But I don't know if we have a nice equation for that anyway. And so, what was behind the scenes? You have to do asymptotics for Schur functions, and one way to do it is to represent it as a complex integral. So if you have just one variable, you can write this ratio of Schur functions as a complex integral. And then you can do asymptotics on that integral to figure out what the behavior of this function is. So that's also, I'm going to leave it just part of the slides without getting into the details of how we do this. So I'll move on to another application and another so I promised generalizations of this symmetric function. So let's look at something different. So these are the factorial Schur functions. It's a multi-parameter family that's generalizing our Schur function, and they actually appear in this paper of MacDonald. What was it? 9 variations. So people do sometimes write papers on the whatever variation MacDonald function because it doesn't have a name. These guys do have a name. So we have a partition mu, k variables, and parameters a, and then we're going to define this as a ratio of 2 determinants. Why is this a generalization of the Schur function? What happens if we set the a's to 0? Here we're just going to get xi to the power of mu j plus k minus j. And this is the Weil determinantal formula for the Schur functions. What other properties do we see from this formula? I mean, is this a polynomial, first of all? It is a polynomial because, so the columns of this matrix, so every whatever, okay, let's say columns are indexed by, correspond to each variable xi, they're the same polynomial here. If you set xi equal to xj, you're gonna get 2 identical columns in that matrix, goes to 0. So, and the determinant, of course, is gonna be a polynomial. It's divisible by all these linear factors, xi minus xj. Okay, so it is a polynomial. What else? Is it symmetric? Yeah, so the top is skew symmetric, the bottom is skew symmetric, ratio is symmetric. Okay. So with the Schur functions, we had something nice, right? It was actually the generating function for a semi-standard Young tableau, so we can write it nicely in terms of monomials. So what can you do with the factorial Schur function? So to tell you, I'll have to define these funny objects called excited diagrams. They're a relatively new invention. So we have a big shape, lambda, and a small shape, mu, the blue stuff. And we're going to slide these blue boxes along the diagonal as long as everything here is empty from blue boxes. So literally think of it as sliding along the diagonals, these blue boxes. They're physical objects. They should not overpass each other. So this is an excited move. And we're going to form all possible diagrams obtained from doing some of these moves. We choose what boxes to move and so on. There is no restriction other than the motion part. So first of all, we start with the starting point is going to be this situation, mu inside lambda. And we can move this box. We get this excited diagram. We can move another box. We get this excited. Or we could have moved the other box here. This one, this one, this one. Don't worry about the Q's at the moment. I'll show you where they show up. And okay, so these are our excited diagrams in this case. And let's take our factorial Schur functions. and evaluate. So for mu, let's take a bigger shape lambda. And actually, there is a way to define a permutation V corresponding to lambda. So if you work with the Grassmannian, you would have seen this. So I'll just show it briefly. So suppose that we have some partition lambda like this. Maybe this is our partition lambda. And let's start moving along the boundary of the partition. It's a lattice path. We can number the steps 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 in this case, or I don't know until where we go, but this. And now we are going to read off a permutation from this by. So I'm always confused which order things go, but one of the two. So we read off first the horizontal steps. 1, 2, 3. Where is the next horizontal step? Is 5, 6, 9. I don't know. Maybe we have a 12 here. So it depends on how large. There is an n here as well. Let's say 12. And then we're going to read the other steps. 4, 7, 8, 10, 11. So we have a permutation which has two increasing subsequences and a descent here. This is what's called a Grassmannian permutation. It has only one descent. And so if we plug in parameters, let's say y1 up to yn minus 1, and we evaluate that the variables are the values, let's say the first sequence of values. So we're going to have y1, y2, and so on, y12 from here. And then if we evaluate this factorial Schur function, it's going to be equal to this sum over all excited diagrams. Okay, so there, and then for all the boxes inside, we do the corresponding differences for the two variables. Again, V is our permutation that we are going to care about. Okay, so what does this have to do with Lozenge tilings? Yeah. So D is another parameter that's involved in the whole thing that we need to set. So mu is a partition inside lambda, and lambda is a partition inside the d by n minus d rectangle.
No, but the quantity that you're computing is not a factorial. It's something different. It's mu d.
So we should remove this. I mean, it's the same factorial Schur function. That doesn't change things, but we need to. I mean, these involved already in here. V1. Okay, so what does this mean? So let's take a shape lambda. Let's take this excited diagram inside. So this is an excited diagram, the partition 3, 2. And we're going to make a Lozenge tiling out of it. So how do we do this? So this box corresponds to the topmost lozenge. And all we are going to do is keep track of how far each box of mu has moved along its diagonal. So this box didn't move. It's going to stay on top. This box, this came from up here, right? So it made one step down. So we are going to put this lozenge one level down. This box also made one step down. We're going to put the lozenge one step down, and then this box made 2 steps down, and then this one is 3. And this also corresponds to a reverse standard Young tableau in this case. 3 to 1 are the positions of these lozenges, and 2 to 0 are this. Okay, so we also are going to impose a grid on top of this picture. So inherently, this is a 3-dimensional picture, but we're gonna consider it flat and put a flat 2-dimensional grid on top of it. Okay. And so these horizontal lozenges, they are going to get weights, which are the differences of the x-coordinate on that grid and the y-coordinate on the other one. Okay, so what does this formula have to do with this picture? Other than, okay, this is an excited diagram involved in here, but we have this parametrization. What do these indices mean? Can we decouple them? And yes, we can. We can, for the sake of overriding actually variables, we can call these guys the x's and these guys the y's, and we have suddenly 2-variable situation. So if we weigh our lozenge tiling with these lozenges, the horizontal ones have a weight xi minus yj. So depending on what values you put for xi and yj, it may have actual probabilistic meaning or not. But in this case, it's just a formal weight. So if this, for example, this guy here has weight x2 minus y3, and the total picture, the total lozenge configuration has this weight. Okay, so everything else has weight 1. So we're going to do this local weights for the lozenges, which depend on where they are located. And now if we plug in values for xi and yj, so for example, xi is n minus I, yj is n minus j, we're going to have these weights, and we simulate, we are going to get this picture. Simulating these lozenge tilings with respect to each one would appear with likelihood proportional to that weight. And as you can see here, it's a little bit more top-heavy, right? So the lozenges are moving up. And here is the uniformly random lozenge tilings that you have seen so far many, many times. So when the weight of everything is just 1. We can do one more simulation. If the base is, if mu is actually the staircase, which means this looks like a triangle. Okay, so ignore this part. It's not even part of the picture. Again, so here are these funny weighted lozenge tilings. And here are the other guys, the uniform ones, if I didn't confuse the two pictures. So it's going to be a different weight. So what can we say about lozenge tilings with that weight? We can count the number, the moment generating function, with the weighted, the partition function for this case. So here is our setup. And if we decouple these parameters over there, so we have x's and y's, then if we go over all possible lozenge tilings in this picture, so the base is mu, we have these, the height as far as these things go. We have these weights for each of these tilings. We are looking at the horizontal ones. Then this actually is a determinant. And the entries in the determinant are given by these rational functions. And where did this come from? It came from the factorial Schur functions. So this determinant, as far as I know, is not a lattice, non-intersecting lattice paths thing, even though usually when we see a single determinant, we think of the Lindstrom-Gessel-Viennot non-intersecting lattice paths. And in this case, it's something else from the factorial Schur functions. And the factorial Schur functions and that formula actually came from Schubert calculus. So there is a lot going on here, and we we don't have a very good unified framework for all of this, so I'm just throwing things at you to look at.
Do you know the behavior on previous picture close to the straight line?
We basically, other than the simulations, we cannot analyze this locally yet. So, okay, so open problem. Of course, so as I promised, there are gonna be open problems throughout. So one open problem is analyze what happens with those weights. The only thing we have is counting them. So. And here is actually, we can emulate plane partitions with this model of base mu and maximal entry D, and then Q to the sum of the entries in this plane partition. So these are going to look things like this. And in this example, very simple example where mu is 2, 1, D is 1, we have all these configurations. We have this polynomial. Again, this turns out to be a determinant, which is due to Krotenthaler, but here are the entries in the determinant. Again, this doesn't come from lattice paths in this case, but one can count plane partitions using lattice paths as well. This is just not going to be that simple as if you are doing restricted mu. Okay, so this is the connection with Lozenge tilings for this formula, but where did it actually come from originally, and what else are these excited diagrams involved in? So let me tell you a little bit about that. But if any questions so far? Okay, so I told you already how to count standard Young tableau of straight shape. What if they're skew? So skew shape means that there is an outer shape, there you bite off the inner shape and you fill in the numbers from 1 up to n in those boxes. They're increasing along rows and down columns and so on. You can do, of course, skew semi-standard Young tableau with the same method. So how many are there? So first thing is we can use this Jacobi-Trudy formula to extract a determinant out of this. Our favorite determinants. This actually comes from lattice paths in some sense, even though when you consider the standard Young tableau, you need to actually do a map here. Then there is, if you know Littlewood-Richardson coefficients, I didn't really talk about it, but these are structure constants for representations of GLN. Then we know we can express f lambda mu as a positive sum of f nus. So for those we have formulas, but these Littlewood-Richardson coefficients don't behave so nicely. And anyway, you have a big formula here, right? You're summing over all sorts of partitions. So that's exponential, the large sum. And what can you hope for? Well, you can do this zigzag example. So if we consider the skew shape that looks like this zigzag thing, this is just the standard Young tableau. If you read it along the entries along this path that you see here, this is just an alternating permutation. 8, 3, 4, 5, so it goes up, goes down, goes up, and these are counted by the Euler numbers. What's the generating function for the Euler numbers? They're transcendental trigonometric functions, so can't really hope that much for those numbers are not nice. So we cannot really expect a nice formula here. What's the next thing we can do? Well, there is actually something close to a Hooke length formula. F lambda or mu is n factorial the number of boxes, but then not a single product of hooks, except we're summing over all these excited diagrams, 1 over the Hooke length, for all the boxes that are actually not part of the excited diagram. So here is again our situation. We can obtain, for example, this excited diagram. What are the hooks? For the white boxes, I've written the hooks, and we count them inside the outer shape. So we just count how many boxes are to the left and to the right, reaching the boundary of lambda. So these are the hooks are written here. And here is what the formula says for this shape. 61, this was one of the Euler numbers. It's 7 factorial, and this 7 factorial divided by either of this is not actually an integer, so you have a sum of rational numbers inherently that sum up to some integer. So what we did afterwards was actually to put more parameters in the picture, so we can do a Q and we can do a factorial Skew Schur function, evaluate 1Q, Q squared, and so on, which is just counting semi-standard Young tableau by their total weight, and we have this formula. So this is like a generalization of the Hooke length formula for the same excited diagrams. So this is an application. Of course, this is an infinite sum. And then we can also do reverse plane partitions of shape lambda over mu. In theory, we could also do plane partitions. We just flip the whole picture. And these are going over a larger subset than the excited diagrams. And again, we have this product of Hooke. So these are, we call them pleasant diagrams because they're just not as exciting. So one can write some identities like that. And I want to, because yesterday the non-intersecting lattice paths formula was very, attracted a lot of attention, and there were questions, are there any other types of this determinantal non-intersecting lattice paths formula that show up? And now I'm going to show you one. So, but any questions so far? Okay, so I'm going to prove that formula over here now. Of course, I'm going to use something that's not, it's not going to be from scratch, but I'll show you what we're going to use. So what are the proofs of this formula? The original thing that came from Schubert calculus again, and these factorial Schur functions. So Schubert calculus is subject of algebraic geometry, so it's quite a different topic. I'll mention something about this a little bit in a few minutes. One can try to do some kind of bijections. We don't really have the complete bijection in the sense that we know that the Hillman-Grassel map that I showed you yesterday is the right bijection. But the proof itself is partially algebraic. So, and then there is the non-intersecting lattice paths. It's my favorite. So here's how it goes. So it's a theorem by Lascaux, Pragatz, and it was generalized by Hamel and Goulden in the following way. So we take a skew diagram, lambda over mu. And actually, the theorem is a lot more general than what I've written here. But basically, if you can cut your diagram in whatever paths you want, as long as they're non-intersecting. So paths meaning that ribbons like this, so consecutive trail of boxes. So in this case, I'm going to use this kind of cut. So we start from the boundary. We cut everything here. Then we go traverse it next with this theta 2, then theta 3, then theta 4, and then theta 5 is a separate little thing. And then the Schur function, as a Schur function with all the variables in it, is equal to the determinant of these other Schur functions that are obtained from these ribbons. Some procedure, but these are ribbons themselves. They are cut off from this big ribbon. Here is an example. If we want to compute the Schur function here, we're going to cut the shape like this. And the determinant is going to be basically defining our ribbons by matching the endpoints of theta I and theta j, depending on which diagonal they are on. So the first entry here is going to be just this ribbon. So we're going to calculate Schur function of this shape. then this other entry is going to be theta 1 sharp theta 2, which means that we get the beginning of this little thing here, but we need to get it on to move it along the diagonal to this point, and then we get the end of the theta 2. So there is a translation of the endpoints going on here. So we get this thing. In the other case, we get the beginning of this and the endpoint of the little thing. And then the last entry is just the little thing here. It's a determinant of these Riemann-Schur functions. This also includes the Giambelli formula. If you cut your shape into hooks, you're going to get exactly the Giambelli formula. If you cut it into rows, you're going to get Jacobi-Trudi. So this is a very, very general formula, and the proof is actually using some kind of lattice paths, but they're who have weird trajectories. They can go up and down. All that matters is that they don't self-intersect, and you have some topological conditions for that. Okay, and now what do? If we have a border strip like the zigzag thing that I showed, and we take a Schur function evaluated at 1q, q squared, and also to infinity, then we can prove that is equal to going over all paths from the start point of this theta to the end point that are contained inside our outer shape lambda. And then we have this local weight for each path. So here is a formula. This is the original theta, and then we go over all possible paths inside this shape. We have a weight of this form, depends on the hooks. So it's a weighted sum over all possible lattice paths. And now we can actually invert the whole thing with lattice paths back. So the thing is to realize is that our excited diagrams, if we cut our shapes in the opposite direction, so first we go from the inside and then toward the outside, whenever we do an excited move, it's just switching a corner of a path from inside to the outside. And that the complement of these excited diagrams are just all the possible non-intersecting lattice paths in this lambda with these starting points. Okay, and now once we realize this all together, we can apply all the formulas. So S lambda over mu is from the one hand this determinant, from the other hand we substitute the value for S theta as a sum over all these lattice paths with the given starting points and then local weights for the points in the path. Then we apply the non-intersecting lattice path theorem from Lindstrom-Gessel-Vienot to realize that if we have determinant of individual lattice paths, in the end we cancel out all the intersections and we just get the non-intersecting lattice paths with those weights. And the final point is to realize that the non-intersecting lattice points with these starting points are exactly our excited diagrams, and we get our formula. Okay, so I have 5-10 minutes. So any questions on this part? So there are two lattice paths going on here back and forth, and they're different. So, all right. Okay, so I promised some more generalization. So let me show you what other things there are without getting much into detail, because I'm also not really working with those objects that much. So one whole little with polynomials, one parameter generalizations of Schur functions. Here is a formula you can write. What does this mean? So this is a rational function in our parameter t. It has an explicit product form. Sum over all permutations of Sn. W acting on this is basically we're permuting the variables. So we take this expression and we plug in, instead of x1, xw1, then xw2, and so on, going over all permutations. So a priori this is going to be skew symmetric, but it turns out, no, sorry, this is actually symmetric, of course. If t is 0, this is exactly the Weil determinantal formula if t is 0. If you write it in terms of expand the determinant as sum over permutations, if t is 1, then these are just going to be the monomial symmetric functions, because this factor is going to cancel out all the repeating monomials. So this function is interpolated between Schur functions and monomials. The Schur functions expand nicely in terms of those guys. These are the Koska-Fulkes polynomials. They have a combinatorial formula. They're non-negative integer coefficients.
I'm sorry, S lambda x doesn't depend on t, right?
Yeah, so the t is gonna cancel somehow in here. But many of the formulas that we show for Schur functions are missing here. So this thing becomes more and more complicated, and there are many problems that we don't really know. We know for Schur functions, but we don't know for these guys. And the next level, we add one more variable, Q, and we get the McDonald polynomials, which are not called McDonald polynomials in McDonald's book, because he was trying to set the stage for people to call them. So he was calling them, generalizations with 2 parameters. So that's where they were introduced in whether chapter 4 or 5. And I'm not gonna write you the definition because it's horrible. And one of the holy grails actually is to prove that the McDonald polynomials expand positively in the Schur functions, positively in the sense that the coefficients, the modified McDonald polynomials, I should say, so remove those factors here in terms of, so the coefficients in the expansions are polynomials in Q and T. With non-negative integer coefficients, and we know this is actually true from some deep representation theoretic reasons, but we don't really have a combinatorial formula for that. Then there are Schubert polynomials, which are not symmetric anymore, except in some cases. And then there are the Grothendieck polynomials. So this is Schubert calculus, this is K-theory related. So this is not really, so everything before was somehow motivated by representation theory, and this is going beyond. So I will tell you a little bit about the Schubert polynomials, just so you have some idea what this looks like. And I'll tell you an open problem. So the Schubert polynomials, they correspond to cohomology cycles of Schubert classes in the flag variety. So you have some algebraic geometry that's governing the whole thing. And how are they defined? So we have a divided difference operator, which is sort of like a derivative, but you're exchanging variables, the ith and I+1 variable, and then dividing by the difference. So as long as this is a polynomial, of course, the result is also going to be a polynomial. And what we do is we set for the maximal permutation, we set the Schubert polynomial to be this monomial. And then we start from there on, to get our permutation of interest, we perform simple transpositions to sort this to our permutation. And then for each simple transposition, we apply the delta I operator. So it's a sequence of applications of these operators to our polynomial. What's not obvious here? So it's obvious we're going to get a polynomial in these variables. What's not obvious is that the coefficients are going to be non-negative integers. And so before I do that, so again, that same type of permutations here, what's called Grassmannian. So it has only one descent. If you plug it, the Schubert polynomial is actually equal to the corresponding Schur function. That same lambda here. So they generalize our favorite Schur functions. but at a restricted set of variables, so the thing is not, well, wouldn't be symmetric. And then there is a combinatorial formula, goes over these guys. These are called pipe dreams or RC graphs. Pipe dreams, there is a computer game from 30 years ago. So it's basically a tiling of this upper triangle with tiles that are either elbows or crosses. And what is the condition is non-local. So this is no longer our type of tiling because we are not allowed to intersect two of these guys twice or more. So they only intersect once. And this is like a global behavioral constraint, and none of the methods that we know so far in statistical mechanics really tell us something about how these pictures behave. And then the Schubert polynomial can be defined as a sum over all these types of pictures going from, if you think of this as the numbers 1 up to n, these are the numbers 1 up to n, and we want to connect the corresponding numbers I with wi and so on. If we look at all these pipe dreams, we get for each one of them, we get a corresponding monomial, which is coming from how many intersections there are on each line. And there are some identities related to that. So there is a McDonald's identity, which going over all reduced decompositions of our permutation, multiplying the indices in that reduced decomposition and weighting by the number of those, so by L factorial. There is a Cauchy identity, so similar to the identities I showed last time. If we take W and then W times W0, so it's like a reflection of the diagram of W. With two variables, you get this nice product formula. And we have a favorite problem associated to this. So how large does this thing get? So if we take our Schubert polynomial, look at all permutations W, and evaluate it at all once. In other words, we are counting all these pipe dreams in the picture. What's the maximal one? How large does it get? And it grows with the exponential to n factorial n squared. So that's the right order to look at. But is there actually a limit of this thing? So we can do, because the number of permutations is just n factorial, which is much smaller than e to the n squared, we can just look at the total number of RC graphs. It's gonna be the same, the leading term is gonna be the same. So we can look at this. How large does it get? Well, Stanley figured it's between 1/4 and 1/2. Because thanks to this identity that I showed earlier, this Cauchy identity. But can we figure it out better, and does this constant actually exist? So this is what we did. We looked at this type of permutation, so they're called layered permutations. We could do the asymptotics here because we have some type of product formulas. And we got that for these permutations, we beat this 1/4, we get 0.29 something. And the real question is this actually the maximum? Maybe, maybe not. All we know is that there is an upper bound which comes from counting alternating sign matrices, which probably gonna show up 6-vertex model with uniform weights. Alternating sign matrices somehow show up in this whole business. Don't ask me exactly why, but then it's bounded above by that, so we have an exponent 0.3 whatever. So this thing lives between 0.29 something and 0.377, and does it actually exist a constant at least? Can we say it converges? It's an open problem. That's it. Thank you.